Yes, a good morning to you, my dear students and all viewers for this learning program. Teacher Kakuru is in the house and I want to welcome you this morning for our lesson. In our last lesson, I want to mention that we were looking at refraction. We looked at application of the n sign I is a constant formula that we called Snails Law, and we looked at real depth and apparent depth method for determining and defining refractive index. Today, I want to challenge you and ask you whether you worked through the numbers I left behind. There were several numbers, and I want to encourage you to continue working through them. We want to proceed and look at critical angle and total internal reflection. In our discussion today, I want to invite you to enjoy the lesson and please remind yourselves what you may not have understood. Critical angle and total and internal reflection are going to be our focus today. And we will begin by considering the following diagrams. We shall use three different diagrams, and one, if I call this diagram A, we shall consider to use glass and air for the reasons I will mention shortly. If a ray is incident from glass at an angle of incidence I, we shall discover that this ray will be refracted and will also be refracted at the same time. The angle of refraction is R, and the angle of refraction, because of the laws of refraction of light, being equal to the angle of incidence, we shall denote it as I. But this refracted ray will be very weak. And the reason why we are using glass to air is because one of the conditions for total internal refraction is that light must move from a dense or to a less dense, or from a more dense to a dense medium. Our second diagram will still be glass to air. All diagrams will be glass to air. But this time, the angle of incidence is going to be let to be equal to an angle which we shall call the critical angle, C. There will still be a refracted ray that is weak. And the refracted ray this time will graze the interface, making the angle of refraction 90 degrees. And this is still glass, and this medium is air. And lastly, our last diagram is when the angle of incidence now exceeds the critical angle, when the I is greater than the critical angle, all the light that is incident will be refracted, giving us a situation that we shall shortly refer to as the total internal refraction situation. Now, our discussion is mainly going to run along these three different diagrams, and we are going to start by looking at diagram 1. I'll put a sentence or two to illustrate or to mention what is happening, but I want to mention that summarily, in figure 1, which I've called figure A, in figure A, the incident ray comes in at an angle I. It is refracted with a weak refracted ray at the same angle following the laws of refraction of light. And the refracted ray is a strong refracted ray making an angle of incidence of refraction r. So in figure 1, we are saying that the angle of incidence is small. The value of I of the angle of incidence is small. The value of the angle of incidence is small, and we notice that light in both diagrams is traveling from glass to air. Light is traveling from glass to air, and there is both refraction and refraction. Both refraction and refraction occur. We have light traveling from glass. Maybe for a record, you may remember that the refractive index of glass is 1.5 and the refractive index of air is 1. That is very important. Later, as we shall notice, that we need to emphasize that the light is moving from a dense to a less dense medium. In figure B, the angle of incidence is further increased to reach an angle that we call the critical angle. The angle of incidence is increased to a value that we call the critical angle. We have a weak refracted ray. I will still say refraction and refraction still occur. But importantly, the angle of refraction is now 90 degrees, as we can see. The angle that the refracted ray makes with the normal is now 90. And that will bring us to conclude that we need to define the critical angle. We have a question here that prompts us to define critical angle. To all the learners following this lesson, we define critical angle as the angle of incidence in a more dense medium that gives the angle of refraction in the less dense medium as 90 degrees. The angle of incidence or we could even say it is the angle of incidence in a more dense medium that causes the refracted ray to graze on the interface of the two media. As you notice from this diagram, the value of the angle of refraction is 90 degrees. For all of you that have been following the physics of refraction, you know, and the mathematics, that this symbol represents 90 degrees. When we go to diagram C, we notice that as we further increase the value of I, there is now no refracted ray, and all the light has totally been refracted. all the light has totally been reflected. So we say as the value of I, as the value of angle of incidence is further increased, as the value of the angle of incidence is further increased, the refracted ray obtained is much brighter. It is no longer weak. Actually, this is a very strong refracted ray. Is much brighter and strong. Or the incident light is now totally internally refracted, a situation we refer to as the state of what we are calling total internal refraction. We have all the incident light, all the light that was incident is refracted without any being refracted or absorbed. And we can now define total internal refraction. We can now define total internal refraction as the type of refraction that is said to occur when all the light incident is refracted in the more dense medium without any being refracted in the less dense medium. All the incident light is refracted in one medium, the more dense medium, that is the glass medium, with none of the light refracted or refracted in the less dense medium. Total internal refraction, as we shall shortly see, will occur when two conditions are fulfilled. And one of the conditions, as we shall shortly see, is that the angle of incidence must exceed the critical angle. As you notice here, we are saying that I is greater than the critical angle. And the other condition is that light must be moving from a more dense to a less dense medium. Very common questions here are they will, in most cases, ask you to define the term critical angle, and they can ask you to define the term total internal refraction, and they can also ask you to state the conditions for total internal refraction to occur. They can ask you to define critical angle, take note. They can ask you to define total internal refraction, and they can ask you to state the conditions for total internal refraction to occur. These diagrams are very, very important, and this concept, again, I will say, cuts across I want to implore my colleagues, the teachers of physics, that it is important to mention that these concepts do not change, especially if you are teaching ordinary level students, so that those that have hope of doing physics at high school should not delete these facts from their mind on completion of Senior 4. Usually some students, if they are not well guided, will assume that physics at A level is very different from what they studied at O level, and when they finish Senior 4, they tend to think that they don't need the information they had earlier. A good teacher will always emphasize what they know will be required by the A-level students who would wish to do physics, and therefore mentioning it would just be adding value to the students, but at the same time to the teacher. I will proceed to bring down these conditions that are necessary for the occurrence of total internal reflection as we proceed with this lesson. I have already mentioned that for total internal reflection to occur, two conditions must be fulfilled. One is that light must be traveling from a more dense to a less dense medium. From a more dense to a less dense medium. And condition number two is that the angle of incidence in a more dense medium, the angle of incidence in a more dense medium should be greater than the critical angle. These two conditions are supposed to be fulfilled for us to attain the condition of total internal reflection. We are going to proceed to look at the relationship between refractive index and critical angle. Between the refractive index, or just simply write the symbol, and the critical angle. Relationship between the refractive index and the critical angle. And I will put a sketch that we are going to use in this space. We are going to use the second diagram that we had, that when light is incident and the value of I is equal to C, we shall simply take this as C. We saw that the refracted ray grazes the interface. I will maintain glass, air, but now that the fact is here that light must be moving from a more dense to a less dense, I will mention confidently that since we know that refractive index of water is 4 out of 3, refractive index of air is 1, refractive index of glass is 1.5, it implies that we could still have total internal reflection occur when light is moving from water to air, or when light is moving from glass to water, or when light is moving from water to air, those three. And therefore, after deriving this relationship, we shall be able to look at those three situations. That diagram is going to help us derive an expression that I will still emphasize is very common again in exam, especially at high school. They can ask students to actually derive this expression. We are going to use the n sin I, which we call Snails Law, using Snails Law formula, which we wrote and we proved here that n sin I is constant. The angle of incidence, first of all, is C. Note that I is equal to C, and the refractive index of glass is known. Therefore, if we look at refractive index of glass, where the incident ray is, times the sine of I should be equal to the refractive index of air, because the angle of refraction is also known, times the sine of R. If I substitute in for I and R, I'll have Ng, the sine of C, which is our I, should be equal to Nm, the sine of 90 degrees. I will be quick to mention that if you pulled out your calculators and you look for the sine of 90, they would give you that it is actually 1. And we are already aware also that any air is also 1. The refractive index of air is also 1. So my Ng, the sine of C, therefore, is equal to 1 times 1. And since our interest is to get the relationship between N and C, it implies, therefore, that Ng, the refractive index of glass, will therefore be equal to 1 out of the sine of C. For one learner, this is valid, but it can also be rearranged to say that if we make sine C the subject, it is still the same as that. Usually, like I mentioned much earlier, they can ask you to prove, to show that for light moving from glass to air, or for light moving from water to air, or for light moving from glass to water, show that the refractive index of the first medium is equal to 1 over the sine of the angle of incidence, which is the critical angle, or the sine of the critical angle is equal to the reciprocal of the refractive index with of the more dense medium. And we are going to consider glass air. To find the value of C for the glass to air situation that we have considered, we know that refractive index of glass is 3 out of 2. If refractive index of glass is 3 out of 2, using this second case, that sine c is equal to 1 out of 3 of n, it would imply that our sine of c is 1 out of 3 out of 2, which automatically implies that sine c is the same as 2 out of 3. And using our calculators, the critical angle will be the arcsine or the sine inverse of 2/3. If you used your calculators to 1 decimal place, this would give you 41.8 degrees. To 1 decimal place, it would give you 41.8 degrees. And we therefore say that the critical angle of glass, is approximately 42 degrees. The critical angle of glass is approximately 42 degrees. That means that should you be using glass and the angle of incidence exceeds this value, then you must obtain total internal reflection. Should you be using glass and you calculate the angle of incidence, or you are given a question and the angle of incidence is greater than 42 and it is glass, total internal reflection must be confirmed to occur. Total internal reflection must be confirmed to occur. I will give an opportunity for the students capturing this information to capture, but I will at the same time take the opportunity to calculate just one more critical value or critical angle of incidence and give the learners one to try out as well. Question. You can be asked to calculate the critical angle. Calculate the critical angle 1 for water. Critical angle for light traveling from part 1, water to air, part 2, glass to water. And here you are given that any air is 1, any water is 4 out of 3, and any glass is 3 out of 2. Like I said, I'm going to work out with you part 1, and I will leave the learners to do the second part. If I choose to use a diagram, I will call this angle the critical angle you are looking for. This medium is water, and this is air. And like we said, critical angle causes light to graze the interface. It causes light to graze the interface, and therefore, the value of I is C, which we are looking for. The value of R is 90 degrees, which we know. The values of the refractive indices are known. So using Snails law, that any water sine of I is constant, it implies that my any water, the sine of C should be equal to any air, the sine of R. But I have C, which I want, and I have R. So if I substitute my 4 out of 3, the sine of C should be equal to 1 times the sine of 90. And if we proceed, our sine of C will definitely be equal to 3 out of 4, since we already saw earlier that 1 times sine 90 is still 1. So we shall cross multiply, and we get our C as the arc sine or sine inverse of 0.75. Using your calculators, you can verify that the arc sine of 0.75 will give you the critical angle as 48.6 degrees. So the critical angle of water to air is supposed to be 48.6 degrees. Caution here, as I usually tell you, that candidates must make sure that their calculators are in the degree mode before they use any trig function. I will ask students out there that are attending this lesson right now, and those that will find it on Facebook, on YouTube, on the different channels and accounts, should try out the critical angle for glass to water. Should try out that number that is asking you to find the critical angle for glass to water. Try that out. Try that out, and basically you need to know that light is moving from glass to water, and you need to use n sine I as a constant, and the rest, if you are systematic and organized, should be able to work out very well. We shall proceed to look at the applications of total internal reflection, and discuss those that we are able to discuss within this meeting today. We shall continue to look at the applications of total internal reflection. Applications of total internal reflection. There are several applications of total internal reflection, and we are going to outline all of them and look at them one by one. The first application is that it is used in totally reflecting prisms. Totally reflecting prisms. The second application, it is used in erecting prisms. Erecting prisms. The third application, it is used in fiber optics. And we can also look at reflection in the ionosphere. Someone can call it in the reflection of radio waves. There are two other contention points that usually come in here. There is the fish's eye view and the mirages. The fish's eye view and the mirages can be looked at. Normally at O level we look at them as applications, but ideally they are situations that apply. They are situations that apply the concept of total internal reflection. So we can add them here. I can add the mirages, and we may not discuss the fish's eye view. I will follow them one by one, or I may not discuss all of them, but I will mention about each of them, time allowing, for today's lesson. I want to talk about the total refracting prisms as the first application. I am aware from contacts and information that I get and feedback that this lesson is attended by very many students and even some parents and teachers. When we talk about totally reflecting prisms as an application of total internal reflection, it implies that total internal reflection prisms are used as reflectors of light. Here we look at prisms being used as reflectors of light. And one would wonder how a prism can reflect light, but I will illustrate here even before I finish that point. I think I will be able to illustrate that when we talk about prisms reflecting light, we are talking about when used in the instrument that we call a periscope. When used in periscopes and also in prism binoculars. When used in periscopes and in binoculars. These are binocular prisms. You will remember that for the periscope, just for purposes of illustration, a periscope looks at the use of plane mirrors. Two plane mirrors are arranged in such a way that they are facing each other. So they are put to face each other, and if you extrapolate, they are supposed to be intersecting at an angle. At the start of the discussion of light, we were able to look at inclined mirrors. That's why when I extrapolate, I want to show you that they're actually inclined at an angle. But if this mirror is turned into a prism, we shall discover a prism is fully made out of glass. We shall consider an isosceles prism that is right-angled. If we consider the 90-45-45 isosceles prism, we shall discover that this type of prism will actually reflect light. If I use this prism here, the 90, 45, 45, and light is incident, this is where I want to emphasize to students, whether O level or A level. They draw a diagram like this, and they clearly tell you that this is 45 degrees, that is 45 degrees, and of course this is 90, and they tell you to complete the diagram to show how light moves. Whenever light is incident normally, it means that this light is not going to be refracted, even if this is air and we are aware this is glass. So light is going to pass through at 90 degrees. Why? Because whenever it is incident at 90 degrees, it passes without refraction. And this light ray is going to be refracted at this point. I want learners that are following this lesson to take note here. It is going to be refracted here, and it is still going to be refracted along there. Now, once this light is refracted, if I choose to do the angle geometry here by introducing a normal, I want the students following this lesson to note, if this is 90, even this is 90, and that means that since this is a right angle triangle, this small one, this will also be 45. Remember, this is now my normal. I can extrapolate it and label it. There is something I want to emphasize here, that if this is 45, the angle between the normal and the incident ray, which is this one, is also 45, because this is 90. And since this angle is 45, and we saw that the critical angle for glass was 42, it means light cannot move out. It can't be refracted. That's the reason why it is reflected here. And we say at this point we are actually having total internal reflection, because this is also going to be 45 degrees. That is why we are saying that one of the applications of total internal reflection is refraction in prism binoculars. We can therefore mention that at this point, if I call it point B, I can say that at point B, we have total internal reflection. We have total internal reflection, if I may use that abbreviation. Why? One may ask, why? And I'm saying because the angle of incidence, I, is equal to 45 degrees, which is greater than the critical angle for glass, which is greater than the critical angle for glass, which is greater than the critical angle for glass, which we of course know is 42 degrees. Therefore, we can say that the 90-45 prism deviates the ray. It deviates because this ray would have continued like that if there was no deviation. So it deviates the ray through 90 degrees as the plane would do. It deviates the ray through through 90 degrees. It deviates the ray through 90 degrees, and because of that, prisms have advantages over plane mirrors that I should mention as our lesson tends to 0. As our lesson tends to 0, allow me mention that there are advantages of prisms over plane mirrors. Advantages of prisms over plane mirrors. Because prisms do not absorb light, they form bright images. They form brighter and clearer images. They form brighter and clearer images since there is no formation of multiple images. Since they do not form multiple images. Remember, with plane mirrors we saw when we are discussing the application of plane mirrors in places like barber shops or hair salons, as commonly called, we saw that you're able to see yourself several times because of the so-called multiple images, and that means that every time light is incident and reflected, part of it will be absorbed. The second advantage is that with prisms there is no loss of light intensity. There is no loss of light intensity. There is no loss of light intensity in a prism at the total internal refraction stage. During total internal refraction, all the light that is incident will be reflected with none refracted, i.e., all incident light is reflected with none refracted. And the last advantage is that prisms do not have silvering, and therefore they do not wear. There is no silvering in prisms. As we are aware, a mirror is formed by silvering or painting one face, and we are aware that this silvering does wear off with time. So no silvering in prisms is required. As is the case in plane mirrors. So if you are asked, as we wind up, you may be asked to state or distinguish. Can use distinguish between prisms and plane mirrors. You can also be asked, as we wind up, to define these terms that we have discussed today. One is critical angle. Two is total internal reflection. You can also be asked to state the conditions necessary for the occurrence of total internal reflection. And you can also be asked to list down the applications of TIR. We have also said they can ask you to derive the relationship between the critical angle and the refractive index of glass or any other media. As we wind up our lesson, I want to continue to thank the parents for taking good care of all the students, our children. I want to thank the management of this broadcasting house or media house, BBS TV or BBS Media, Uganda Kingdom Media Group. I want to thank the gentlemen behind the scenes. Well, behind every successful man, they normally say there is a woman. And behind every successful show you watch on TV, they are producers, they are gentlemen on camera, they are teachers, and there's a lot of preparation that may not be actually noted by the public out there. I thank them. I want to continue to thank. I have made it a part of my lessons. I want to thank all my students, the ones that are following up my work on YouTube. Encourage you to continue following up. The ones that are following my work on Facebook, Let's Learn from Home, continue. I'm determined to continue doing my best. Like Agnes Nandutu says, I am determined to aspire to inspire before I expire. And I want to encourage you to keep reading. God bless you. Enjoy your weekend. Stay at home and keep safe.